Welcome to today's video, Mastering the Gibbs Free Energy Equation with Miss G. Good morning YouTube, and welcome to today's video on the Gibbs Free Energy Equation. Now this is a really useful equation because it tells us whether a reaction is going to be feasible at a certain temperature, and it's important that we appreciate that the feasibility of a reaction is dependent upon not only the enthalpy change, i.e. whether the reaction is exo or endothermic, but also the entropy change, which is a measure of the disorder of the system, which might increase or decrease depending on what type of reactants we have and what state those reactants are in, and what type of products we are making and what states of matter those products exist as. The feasibility is also dependent on the temperature, and those three properties are then linked by the Gibbs Free Energy Equation, which is given here. So delta G, which is the symbol that we use for the Gibbs Free Energy, is equal to the value for the enthalpy change, delta H, minus the temperature, T, times by delta S, which is the entropy change. And the magnitude of the value that we get for delta G tells us whether this reaction is going to be feasible. So to be feasible, delta G needs to be less than or equal to 0. If delta G is positive, the reaction is quite simply not feasible. Now, in terms of the units of these variables in this equation, delta H and delta G are both measured in kilojoules per mole, but when we calculate the entropy change, those values have units of joules per Kelvin per mole. So before we do any calculations involving the Gibbs Free Energy Equation, we need to convert the entropy value to kilojoules per Kelvin per mole by dividing by 1000, and temperature should be in Kelvin. If it's provided in degrees Celsius, we would add 273 to get that into Kelvin. So let's have a look at an example question and see how we can implement this. So I have this equation here where sodium carbonate is decomposing into sodium oxide plus CO2. Now, this is an example of thermal decomposition, and thus the value for delta H is positive because this is an endothermic reaction. So the value for delta H is plus 323 kilojoules per mole. Because we are going from 1 mole of a solid in the reactants to 1 mole of solid and 1 mole of gas in the products, there is an increase in the disorder of the system over the course of this reaction, and thus we would expect the entropy change to be positive, which it is. It is positive 153.7 joules per Kelvin per mole. Now, before I go on and do anything with my calculation, I personally would always do the conversion of that entropy change value into the kilojoules per Kelvin per mole first by dividing by 1000, which gives me 0.1537. And this is often the part that students forget to do. And then we've been given a temperature at which this reaction occurs of 1200 Kelvin. And what we're actually being asked to do is to say whether this reaction would occur at that temperature. So is this reaction feasible at 1200 Kelvin? So all I need to do is sub my numbers into my Gibbs Free Energy equation. So delta G is equal to delta H minus T delta S. So 323 take away brackets 1200 for the temperature times by delta S in kilojoules per Kelvin per mole. That gives me a positive answer of 184.44 kilojoules per mole. And because that value is bigger than 0, delta G being bigger than 0 means that this reaction is not feasible at 1200 Kelvin. What lots of questions will then ask you to do is to determine the temperature at which the reaction does become feasible, because it's no good, thinking from an industry point of view of knowing that a reaction is not feasible at a certain temperature. It's quite important that we know at what temperature it does become feasible. So in order to work that out, we set delta G to 0. Why? Because delta G being equal to 0 is the first point at which the reaction would be feasible, because delta G being 0 or negative equates to a feasible reaction. So we're going to set delta G to 0, and then we can rearrange the Gibbs Free Energy equation to make T the subject. So 0 for my value for delta G would be equal to delta H minus T delta S. I'm going to take the minus T delta S over to the left-hand side so it becomes positive, and then I'm going to divide through by delta S to give me temperature equals. And then again, we are subbing in the same numbers that we had previously for delta H and delta S, and that gives me a temperature of 2101.5 Kelvin. So that is when this reaction would become feasible. So it's not feasible at the lower temperature of 1200 Kelvin, but it is feasible if I were to increase the temperature to 2101.5 Kelvin. And it would remain feasible at any temperature above 2101.5 Kelvin, because at that point, delta G would start to become negative. Here, delta G is 0 at that temperature there. If I increase this temperature, delta G would start to become negative and get more and more negative the higher the temperature that I used. So we can summarise, as I've done in this table, all the different options, I suppose, for what values we have for delta H, what values we might have for delta S, and what that would mean for our values for delta G. So delta H could be either negative or positive, depending on whether the reaction is exothermic or endothermic. The entropy change can either be positive or negative, depending on whether there is an increase in the disorder of the system over the course of the reaction, as we saw earlier, or whether there is a decrease in the disorder of the system caused by, for example, gaseous reactants becoming solid products, or potentially there are more moles of gas being turned into fewer moles of gas within our reaction. And we can see how that impacts on delta G. So if we have an exothermic reaction and we have an increase in disorder of the system, delta G would always be negative, and thus that reaction would always be feasible at any temperature. And whilst you could learn this table, I think it's far better if you are able to deduce that using the Gibbs Free Energy equation. So if delta H is negative and delta S is positive, a negative number take away a positive number is always going to give us a more negative number. Hence delta G will always be negative, hence the reaction will always be feasible. The complete converse of that is the bottom row of my table here. If the reaction is endothermic and delta H is positive and the entropy change is negative because there's been a decrease in disorder, this reaction would never be feasible, because we'd have a positive number take away a negative number, which would turn that into a positive. So it'd be a positive number adding a positive number, meaning that delta G would always be positive, and thus that reaction would never be feasible, or it would always not be feasible. Now, the middle two combinations are feasible at certain temperatures, but not at others. And we've just seen one of those examples here. With this thermal decomposition reaction, it wasn't feasible at 1200, but at higher temperatures, it became feasible. So anytime you have an endothermic reaction, but there is an increase in the disorder of the system and delta S is positive, it can be that delta G would be negative, but that will only occur above certain temperatures, because if delta H is positive and there is an increase in disorder, we need the temperature to be above a certain value to make this positive for the T delta S value bigger than the delta H positive. Conversely, if we have the reverse combination where the reaction is exothermic but there's a decrease in disorder, delta G again can be negative, but it would only be negative below certain temperatures. If delta H is negative and delta S is negative, then the negative and the negative would make this part a positive. So at this point, we need T delta S as a positive value to be smaller than the value of my negative value for delta H, because if this is too big, then delta G would become positive. Now, those two final examples can be illustrated using these graphs here. So the Gibbs Free Energy equation can be plotted as a straight line graph using the y equals mx plus c equation. And for those of you who have watched my Arrhenius equation videos will be familiar with what we're doing here. So the equation for a straight line is y equals mx plus c, and then I have rewritten out the Gibbs Free Energy equation. I've just changed the delta H from the front to the end so that it's easier to match up with the variables in the straight line equation, and we can see that we're going to plot values for delta G on the y-axis against values for temperature on the x-axis, and that means that the gradient of the line will be equal to minus delta S, and the y-axis intercept would be equal to delta H. So there are two potential graphs that we can draw. The first represented option B in the table over leaf, where we had an exothermic reaction but a decrease in disorder. And the second graph was option C in the table over leaf, where we had an endothermic reaction but an increase in disorder. And we can see when we plot these straight lines that the point at which the line crosses the x-axis represents the temperature at which delta G is equal to 0. Now, for this reaction to be feasible, we need delta G to be 0 or less than 0. So the only time the reaction is feasible is on that x-axis line or below that x-axis line. So we can see on the graph on the left here that anything below that temperature there, the reaction is feasible. At that temperature there, the reaction is also feasible, but at any of these temperatures above there, reaction is not feasible because delta G is positive. Conversely, on this graph here, anything below the x-axis line, the reaction is feasible because delta G down here is negative. At that temperature there, delta G is equal to 0, so also feasible, but below that temperature, delta G is positive. So up here, at these lower temperatures, reaction not feasible at all. So those graphical representations help us to see exactly when these two types of reaction become feasible or stop becoming feasible. Hopefully that's been helpful. Thank you so much for watching. Any questions, as always, please feel free to leave a comment on this video or contact me via social media. Thank you. Thank you so much for watching. I hope you found it helpful.